In this problem, we are going to combine electric forces, electric fields, Newton's second law, and kinematics. So 2 things from last semester and 2 things from this semester. Now, tiny droplets acquire a small negative charge while dropping through a vacuum in an experiment. A similar experiment to this, called the Millikan oil drop experiment, is how the physicist Millikan was able to determine the fundamental unit of charge, which is the fundamental charge of an electron. So we're going to work through a problem that uses similar principles. So we have an electric field here. This is my electric field. These are my electric field vectors, and they're pointing downward. So my electric field is in the negative y direction, and it has a magnitude of 5.92 times 10 to the 4 Newton per Coulomb. For the first part of our problem, we have a particular droplet, we'll call this part A, that is observed to remain suspended against gravity. We're going to have a little droplet of oil in this electric field, but it is observed to hover, to float, to be suspended against gravity. If the mass of this droplet is 2.93 times 10 to the minus 15 kilograms, find the charge carried by the droplet. Q equals question mark. And for this particular case, our oil droplet is suspended. So that means that its velocity is 0, right? And its acceleration is 0. Now, in order to solve this problem, guess what we're going to do? We are going to draw a free body diagram. And hopefully you remember free body diagrams from last semester. So with our oil droplet, we have, this is our oil droplet right here. It's got its weight pointed downward. That's its mass times gravity. In order for it to be suspended against gravity, it has to have an upward force that is equal but opposite to the weight of this droplet in order to keep it stationary, to keep it from moving. So we've got to have an electric force that's acting in the vertical direction. Okay. So this is our free body diagram for this mass. We're going to use this information here, F equals ma, Newton's second law, in combination with our equation for electric force and electric field in order to get the charge on this particle, on this mass. For Newton's second law, for this mass, we've got the sum of all of our forces in the vertical direction equals the mass times the acceleration in the vertical direction. But for this problem, we are going to be suspended against gravity. We have no acceleration, okay? So then we have that the electric force, and we're only going to be operating in the y direction here, so I'm just going to say that this is in the y direction, and I can remove my vectors, minus the weight of my mass, minus mg, has to equal 0. Now, what is the electric force that's acting on my particle here? Well, we can remember that the equation for an electric field is equal to the force per unit charge experienced by the mass. So our electric field is going to be equal to our electric force per charge. We can rearrange that to say that our electric force is equal to our electric field times the charge. So here where I have my electric force, I can replace it with my electric field in the y direction times q minus mg, and that has to equal 0. Now we want to solve this equation for q, so I can move this term to the other side. My electric field in the y direction times Q is equal to mg. Divide both sides by the electric field. Q is equal to mg divided by my electric field in the y direction. Okay. So then my mass was 2.93 times 10 to the minus 15 kilograms. And gravity, that's our acceleration due to gravity on our planet, surface gravity of our planet, that's 9.8 meters per second squared. Okay, and then we can divide that by, now the electric field in the y direction is negative. Okay, negative because it's pointing downward. So this EY component, that's the y component of my electric field vector, is going to be negative 5.92 times 10 to the 4 Newton per Coulomb. We're running out of room here, so I find that this charge on my mass, in order for it to be suspended against gravity, is going to be minus 4.85 times 10 to the minus 19 coulombs. All right. Now, if I take this and I divide it by the fundamental charge, which is 1.6 times 10 to the minus 19 coulombs, this charge is also 3 fundamental charges. So this mass has a fundamental charge of 3 times negative 1.6 times 10 to the minus 19 coulombs. So we could say that that mass has an excess of 3 electrons compared to a neutral mass. For part B of this problem, we are going to have another droplet of the same mass. So its mass is also 2.93 times 10 to the minus 15 kilograms. And it is going to fall 10.3 centimeters from rest. So we'll say initial y position is 0 meters. Its final y position, it's telling me is 10.3 centimeters, or I'm going to write that as 0.103 meters. It's falling from rest, so its initial velocity was 0 meters per second. And it's going to fall this 10.3 centimeters from rest in a time of 0.25 seconds. Find the charge carried by this droplet. Q is equal to question mark. All right, so we know something about the mass of this oil droplet. We know something about its motion and how long it takes to execute that motion. And with that information, we need to find Q. Because this mass is moving, we know it's going to have, well, if it's starting from rest and it's falling, we know it's going to have a non-zero final speed after it falls 10.3 centimeters, and it's going to have some acceleration. So it's not going to be suspended like our mass was here in part A. What we have to do is still do this similar process with F equals ma, but now our acceleration is not equal to 0. And we have to calculate what the acceleration is with the kinematics problem, and then we can plug that into this equation right here for F equals ma. So the first thing that we'll do then is find the acceleration of this particle as it's falling. Now, these equations are not on your equation sheet for this semester. Our equation for motion is going to be our final y position equals our initial y position plus our initial velocity times time plus 1/2 times our acceleration times time squared. Now we set our initial y position to be 0. You can always set your y to equal 0 position wherever you want, but it makes sense to just say y is equal to 0 where we're starting to track this particle or this mass. Our final y position we have right here. It's falling, so actually we could set y is equal to 0 meters right here. It's going to fall, and then we could say our y final is equal to actually negative 0.103 meters because it's falling. Its position is now downward from where it initially started, so we'll give that a negative quantity here. Okay, so actually maybe we'll say y final is negative 0.103 meters. Our initial velocity was 0. We know the time. We need to find the acceleration of this particle. So if we solve this equation here, y final is equal to 1/2 at squared. Solve this for a. Okay, we can multiply both sides by 2, divide both sides by t squared. So our acceleration is equal to 2y final all over t squared. And that will equal 2 times minus 0.103 meters. This is negative because our particle is falling. And then our time it takes for the particle to fall this distance is 0.25 seconds squared, right? And that gives us an acceleration of minus 3.3 meters per second squared. Now we can use that into our equation for Newton's second law. We've already written it here. We've got that the sum of our forces in the vertical direction is equal to the mass times our acceleration in the vertical direction. This time, our acceleration in the vertical direction is not 0. It's this number right here. On the left side of this equation, we still have our electric force in the y direction minus mg is equal to m times acceleration. And our electric force, we saw we could rewrite as the electric field, the y component of the electric field, times q minus mg, and that equals ma. To solve this equation for q, I'm going to add mg to the other side, and then divide by my y component of my electric field. Q is equal to ma plus mg all divided by the y component of my electric field. And I'm actually going to fancy this up. I'm going to factor out the m times a plus g all divided by my y component of my electric field vector. Okay, we plug in our mass of our oil particle, oil droplet. We've got the acceleration of its motion minus 3.3 meters per second squared plus g, 9.8 meters per second, and we divide it by the y component of the electric field. Now our y component of the electric field, because it's pointing downward, is minus 5.92 times 10 to the 4 Newton over Coulomb. So we plug all that in. This time, the charge on our oil droplet is minus 3.22 times 10 to the minus 19 coulombs. And if I wanted to divide that by the fundamental charge, I would see that this mass has an excess of two electrons. It has a charge of 2 times negative 1.6 times 10 to the minus 19 coulombs. So if it originally started out as a neutral oil droplet, it now has an excess of 2 electrons. And with that problem, we were able to combine part of what we did from last semester and part of what we're doing from this semester, thinking about Newton's second law, thinking about kinematics, and thinking about electric forces and electric fields all in one problem.